gray metal is so light, it floats on water, so soft, you can cut it with a butter knife. So reactive, if it touches water wrong, it can catch fire on contact. And yet, it's inside the phone in your pocket right now, the car in your driveway, the pacemaker keeping someone's heart alive. 1 kilogram of it can store enough energy to power a home for hours, but before it can do any of that, it has to survive one of the strangest journeys of any material on Earth. It starts as a rock, or a puddle of pink brine in the middle of a desert, and somehow ends up thinner than a human hair, wound inside a battery, powering the modern world. That shouldn't be possible from something this unstable. So how do we turn an element that can burn on contact with water into the thing that powers your phone all day long? Let's step inside and find out. Lithium never shows up on its own. It's always hiding, locked inside hard rock or dissolved invisibly into salty water beneath some of the driest deserts on the planet. In fact, it's so reactive that in nature it almost never exists as a pure metal at all. It's always bonded to something else, waiting to be pried loose. There are 2 ways to find it. The first is hard rock mining, where a mineral called spodumene is blasted and crushed out of granite in places like Australia, which alone supplies close to half the world's raw lithium. The second, and far stranger, is brine extraction. Underneath salt flats in places like Chile and Argentina, ancient underground lakes hold water saturated with dissolved lithium, pumped up from hundreds of meters below the surface, in a region so dry that some parts haven't seen meaningful rainfall in recorded history. Workers pump this lithium-rich brine into massive shallow ponds spread across the desert floor, some covering more square kilometers than entire cities, arranged in a checkerboard of turquoise and green that's visible from satellites in orbit. Under intense sun, the water slowly evaporates over 12 to 18 months, turning the liquid a deep turquoise, then yellow, then a strange shade of pink as the mineral concentration rises and different salts crystallize out at different stages. What started as a thin, salty liquid is now a thick brine, up to 30 times more concentrated in lithium than when it began. Meanwhile, in hard rock operations, the spodumene ore takes an entirely different road. After blasting, it's crushed into gravel, then ground down into a fine powder. That powder is mixed with water and chemicals in a process called froth flotation, where air bubbles are pumped through the slurry. The lithium-bearing particles cling to the bubbles and rise to the surface as a froth, while the waste rock sinks, separating valuable mineral from ordinary stone, using nothing more than air, water, and the right chemistry. The concentrated spodumene is then roasted at over 1,000 degrees Celsius, a step called calcination, which cracks open its crystal structure and makes the lithium inside chemically accessible for the very first time. Here's the strange part. It can take almost 2 years of sun, wind, and evaporation just to concentrate enough lithium brine to be worth processing. And a single miscalculated pond can lose months of work to a flash flood or an unexpected rainstorm rolling through one of the driest places on the planet. Entire seasons of evaporation undone in a single afternoon. Either way, brine or rock, the raw material is now ready for the next transformation, turning a rough mineral concentrate into something pure enough to trust with your life. But concentrated isn't the same as pure, and pure is where things get dangerous. This is the stage where one wrong measurement can ruin an entire batch, because battery-grade lithium has to be over 99.5% pure. Anything less, and it can cause a battery to fail, or worse, catch fire. The concentrated brine or processed ore now enters a chemical plant where it's treated with soda ash, sodium carbonate, in carefully controlled reaction tanks kept at precise temperatures and pH levels. Even a small swing in either direction can throw off the entire reaction. The lithium reacts with the soda ash to form lithium carbonate, a fine white powder that looks almost like flour. This powder is filtered, washed, and dried in industrial dryers, running at precisely controlled temperatures. For lithium destined for batteries, it goes one step further. converted into lithium hydroxide through another reaction, then purified again to strip out even trace amounts of calcium, magnesium, iron, or boron, each measured in parts per million, a level of precision closer to pharmaceutical manufacturing than traditional mining. Engineers test the powder constantly, sometimes multiple times per batch, because even a fraction of a percent of contamination can be the difference between a battery lasting 10 years or failing in 10 charges. This white powder, the entire reason your phone survives a full day, starts its life as either a rock blasted out of a mountain or a puddle of pink water baking in the desert sun for a year and a half. Two completely different journeys, ending in the exact same fine white crystal. Once it passes purity testing, this refined lithium powder is bagged into airtight containers, sealed, and shipped to battery manufacturers around the world, where its most important transformation is still ahead. Now it has to become something that can survive being charged and drained thousands of times without ever giving up. A battery cell has to survive being fully charged and drained over 500 times, sometimes more than 1,000, and still hold most of its original capacity. That kind of durability starts with something as delicate as spreading paint. The purified lithium compound is mixed with other materials, cobalt, nickel, or manganese depending on the battery type, to form the cathode and combine with graphite for the anode. Each formula is a tightly guarded balance between energy density, cost, and how many times the battery can be recharged before it starts to fade. These materials are mixed into a slurry, then spread in a layer just microns thick onto rolls of copper and aluminum foil using huge industrial coating machines running around the clock. The coated foil is dried, compressed under enormous rollers to pack the particles tightly together, then sliced into razor-precise strips in a clean room where a single speck of dust can ruin an entire roll. These strips are layered or wound together with an ultra-thin separator between them, a barrier thinner than plastic wrap that keeps the two sides from short-circuiting while still allowing lithium ions to pass back and forth. The whole stack is sealed inside a metal casing, injected with electrolyte fluid and charged for the very first time in a process called formation, where the battery essentially wakes up for the first time, forming a thin protective layer inside that determines how long it will last for years to come. That paper-thin separator is doing one of the most important jobs in the entire battery. If it fails or gets punctured, even by something as small as a stray metal particle left over from manufacturing, the two sides can touch. And that's the exact failure that causes battery fires you might have heard about in the news. Once it passes formation and safety testing, the cell is ready to be packed into a battery pack for a phone, a laptop, or an electric vehicle, alongside dozens or even thousands of identical cells working in perfect coordination, each one wired together with sensors that constantly monitor temperature and voltage to keep the whole pack balanced and safe. And the story doesn't end when the battery dies. As electric vehicles and phones reach the end of their life, the lithium inside them can be recovered. Old battery packs are shredded down into a mixed metal powder called black mass, which is then chemically processed to pull the lithium, cobalt, and nickel back out, sometimes recovering over 90% of the original material, ready to be refined all over again into brand new batteries. Some facilities can process an entire dead battery pack in under an hour, turning what looks like scrap metal into the exact same pure white powder this whole journey started with. The same atom of lithium can end up powering a phone, then a car, then a phone again, years apart, without ever leaving the supply chain. None of this is cheap or fast or simple. Extracting a single ton of lithium from brine can take up to 500,000 gallons of water in a region that barely has any to spare, which is why some of these mining operations have become as controversial as they are essential. And global demand for this element has grown so quickly that the entire industry has had to scramble to keep up. Electric vehicles alone are expected to need many times more lithium within the next decade than the world produces today. If stuff like this messes with your head a little, in a good way, this is exactly what we do every week. Hit subscribe so the next one finds you. So that's the full journey. A rock blasted out of a mountain or a puddle of pink brine baking in the sun for a year and a half. Refined down to a white powder, purer than almost anything else manufactured on Earth. then spread microns thin, wound tight, and sealed into a cell built to survive thousands of charges, and eventually recycled to do it all over again. All of it just so the phone in your pocket makes it to the end of the day. Precision, patience, and chemistry most of us never think about until now.